Okay, sir. Okay.
Yeah. So good afternoon to all of you, and I thank the ATAL sponsored FDP program conducted by Department of Mechanical Engineering, Adi Shankara deemed to be University, and then Professor Michael, the professor from Adi Shankara University. So now today we will start this talk about different approaches in CFD to solve solar thermal system problems. Okay, so in the title, whatever already mentioned, it is the problems is mystery, innovative approaches in CFD to solve solar thermal systems problems. Okay, so first, so there are a number of solar thermal systems are available in the present market. So we worked almost three systems. So those three systems, 3 to 4 systems, we are working on that. In that 4 systems, how the CFD techniques can be used, and then accordingly, how can we solve some critical problems without much experimental work. Like that, we need to see in this presentation. So before that, this is solar related work. Therefore, we need to aware about this, the global solar installation and then PV installations. And then we can aware on that. We can also start similar type of work on solar PV panels or the other renewable energy systems. You can see on that from 2015 to 2024 data here, how the annual global PV installations are increased in the last few years. And then now the values are increased almost to 650 gigawatt, 650 gigawatt. And then China is topping. You see the red color is China. And then India is somewhat a brown color is mentioned. So China anywhere, everywhere they are topping, whether it's a technology or development or power generation. So similarly, solar productions also they are doing good, and they are installing PV panels wherever the possibilities are there. Almost all the desert areas, hill areas, river areas, lakes, and then unused lands, wherever the possibilities are there, there they are installing their PV panels, and then they are always generating the electrical power. So this is actually they are acting as one of the example how to use the electrical energy, how to get the electrical energy from these solar PV panels. You can see in this table, the China is almost giving 609.921 gigawatt power in 2023. Actually, recent report we don't have. I tried already, but I couldn't get on that. And then you can see USA and then Japan. US is the next one. You see just 140 only, 140 gigawatt. We cannot tell some mistake about the USA and then other countries because their solar installation also less. Okay, China's solar installation is good, and then India's solar installation insolation, that means solar flux, whatever we received in the earth, also good. But China is giving 609 value, but India is only 73 value. Okay, the recent value, I think the next PPT, next page, there is the recent report is there, 2024 report is there. But still, you can imagine here how China is, how India is, how much far behind China. Okay, so this awareness we need, but the India's development on the from 2014 to 2023, it's a phenomenal development, but still we need to improve very lot. So we need to get it how we are much far from the other countries, and then how we need to increase again more solar opted systems. So here, yeah, one more chart is given how the solar power installed capacity in India. It is mentioned in megawatt, or otherwise you can take in gigawatt also. From 2018, it is 22 gigawatt. And then it is 2019, it is 29 gigawatt. It is increased to 35 gigawatt in 2020. 2021, it is 41. 2022, it is 53. and then 2023 it is 66 gigawatt, and then 2023 it is 72 gigawatt. This value and then this value is almost matching. India is 73 gigawatt, though I have taken the values from different sources, but anyway, the values are matching. It shows that it is approximately correct. So now they are telling the installed capacity growth of 12.78 gigawatt on YoY basis. That means year on year basis. So like that, India is doing fine, but still comparatively China, uh, we are still very far on that. And now I have got how the Indian states are performing well. One thing is the Rajasthan is performing well. You see, the Rajasthan is the topmost state which is producing more solar energy from solar PV panels, which is almost 17.839 gigawatt of power. Okay, now you can compare with the different states. Some states are huge and then some states are very less. What may be the reason? The northeastern states are very less. So can anyone say what is the reason? Their solar installation will be less. Okay. Like Assam, Arunachal, Nagaland, Manipur, Bihar, Bengal. So there are some certain states, their solar insolation will be very poor. But there are certain states, their solar insolation is very good. All the southern states are very good for solar insolation. Rajasthan and then even central India also. Central India means Maharashtra, Madhya Pradesh, Odisha, uh, Gujarat, Rajasthan also doing good. So the Rajasthan, we know already we have a very good desert lands, a large desert lands. You know the Tar desert is there in the Rajasthan. So that is one of the reason there is the insolation is huge, and then government is also taking huge steps to convert all the solar energy in terms of electrical energy. So they are doing good. Could you look at which other state is doing good on that? Gujarat. Gujarat is doing second. I think Gujarat is second one, 10.133 gigawatt. And then Karnataka is doing good, 9.05 gigawatt. Actually, the undivided Andhra means Telangana and Andhra Pradesh. Actually, Telangana came in 2013 or 2014 only. So if it is undivided, Telangana, Andhra together, then their contribution is more. You see, almost 9 plus. So it is more than Karnataka. And then what about Tamil Nadu? Tamil Nadu is around 7 gigawatt. Okay. So it shows that still some states are doing good, some states are still lagging. Then the conclusion here is we need to do more solar installations and then we need to extract more solar power from because it's one of the free source of energy, zero emissions, abundantly available. So we can extract. At present, whatever we are extracting, the energy is very less. It is less than 0.0001 percentage only. So we can increase our count and then we can also dominate other countries. Okay, so the total is around 70.096 gigawatt. This value is almost matching with the previous two charts. This is 72 and then here also it is 73 gigawatt. Okay, so now before wanted to go to the topics, whatever we are working. So before going to the CFD techniques, we wanted to know what are the physical significance of these topics, what it is, how it is useful to the society, what are the components of the system. These things we can check on that, and then we will go how to solve the problems by using CFD. So first of all, we have developed a solar dryer, and that's why I am explaining why this solar drying is important. So you know, solar drying means the process of thermally removing moisture from porous materials such as foodstuffs, ceramic or clay products or wood can be called as drying, solar drying. Any food products, if we need to remove the moisture by using the heating process, then the product will be getting heated and then the moisture will be removed is called drying. Usually the drying consists of two main processes. If you see the diagram, let us assume there is a brick, rectangle brick. The heat will be absorbed by the brick and then the brick will be losing its moisture. Initially, the moisture will be removed from the surface of the brick called process 1, and then the moisture will be diffused from interior of the object to the surface of the object. That is called process 2, and then again from the surface of the product to by process 1. Okay, so like that, the mass transfer is taking place. Mass transfer or moisture transfer almost the same only. And then we need to know the importance is on that. Totally 9 to 25% of the energy is used for drying applications. So you can understand how much energy consuming process we are doing in drying process. The other importances are to prevent the growth and reproductions of microorganisms. Anyway, if the moisture is more in the food products, then definitely the bacteria and then fungus will be grown and then it will be unusable. Therefore, we have to reduce this growth and reproductions to make the product sufficiently strong and rigid. If you take all the building materials, when you remove the moisture from the building materials, then it will be strong and then very rigid, and then it can be installed for flooring or wall purpose. And then to reduce the weight and volume of the material, most of the cases we are drying the food products to reduce the mass and then volume. For example, the paddy straws. In villages, we are drying the paddy straws, and then once the moisture is removed, we are storing in a secluded place or in the corner of a paddy field, and then it can be usable for year round. 1 year they will use, and the next year again they will get next round of paddy straws. To minimize the physical, chemical, and nutritional changes, we need drying. So you can see there are a number of materials are dried. There are agricultural and food industry like drying of potato, apple, cassava. Cassava means you know that it's a uh, the correct name is in Tamil it is Maravalli Kilangu. Capiaco. Its other name is called capiaco. Green peas, mango, onion, fish, pumpkin, broccoli stems, barley, oats, coffee, black pepper, etc. Still a lot. I'm mentioning whatever the available data from the literature I have taken, but still there are a lot of contents are dried in the open sun drying, in the solar drying, or in the indirect dryings. And then bio-oil industries like drying of peanuts, sunflower seeds, soybeans, rapeseed, canola, coconut, etc. And then you can see the drying of in Andhra and Telangana is good for chili productions, red chili productions. Red chilies are dried. Apple is dried here. Fish is dried here in this picture. So now we will see how the products are dried through solar drying. So there are three main types are there. One is open sun drying, and second one is direct or solar drying. Third one is indirect or indirect solar drying. Okay, in the open sun drying, you may be aware on that. Anyway, now in our home also sometimes we are drying some food materials in the rooftop, like paddy, wheat, masala items, chilies. Okay, these are the items, even dried vegetables. We are drying vegetables also. Like that, you can see in the Andhra and then Telangana, some of the rural areas, the people are drying their paddy, corn, wheat, even vegetables also, like mangoes. They are drying mangoes also because mango production also good in Andhra and Telangana. So they are putting in the open air on the road, highway roads. Part of the road they will take and then they will dry on the roads. You can see this is the image I taken in one of the roads only. Like that, if you see some secluded area, it cannot be possible in the main highways or cities. Maybe some highways related with the rural areas. There they are doing such type of drying, open sun drying, because the people don't have facility to dry the same thing in their rooftops. That's why they are drying in this way. Okay, so this is one of the ancient drying. Not only now, even 400 years before, 500 years before, or 1,000 years before, we are drying food materials in this way. But one thing the disadvantages of this open sun drying. Okay, so there are a lot of disadvantages. One thing is frequent disturbances from animal and then birds. And then if immediate rain is coming, then we cannot safeguard all the food products because you can see the food is dried almost some distances, more than 50 to 100 meters. Very immediately, you cannot safeguard. That is another issue. And then the dust particles will be accumulated on the food products. That is another issue. It may not be, the final products may not be very fresh because it's since it's put in the air or on the road or in the open land or in the rooftop, definitely dust particles will be occupied. And then along with these three disadvantages, another one major problem is on that the color degradation will be there. The natural color of the product will be vanished or destroyed in this open sun dry. The reason is these products are directly getting sunlight exposure. Okay, it's directly exposed by sunlight. If the product will be directly getting exposed by sunlight, then the color degradation will be there. So this is one of the problems. So if you are using for our own purpose, then we can use on that. Sometimes if you wanted to marketing the dried products, then the customer always will be liking on that. The natural colors must be retained. Then he is liking more. Okay, so then in that case only for avoiding these 3-4 limitations, people found the next drying method called direct solar drying. The direct solar drying means it's a simple box setup only. In the top, we are keeping the glass plates. The work of the glass plate will be collecting the solar energy and then transmitting the solar energy inside the product. That is the only job. The glasses are normal glasses only, normal window glasses. Its duty is it will be collecting the solar energy and then it will be transmitted inside on that. So in this direct solar drying, the limitations whatever we faced in the open sun drying is avoided. Okay, what the limitations, the disturbance from animal bats and then immediate rain and then the dust particles accumulation. These three limitations were overcome in this direct solar drying method. But the fourth limitation, that is the color degradations could not be overcome in this setup because here also the solar light will be collected by glass plates and then directly passed out on the food products because here the food products are kept, you can see it's, I think chili is kept inside, red chili is kept inside. So in that case also, the red chili is getting a direct exposure of sunlight. So in this case also, the color degradations will be there. So now for avoiding these limitations in the direct solar drying, people found another method called indirect solar drying. So here, the food products are kept here. You can see this is called the solar air collector. This inclined part is called the solar air collector. And this is called the drying chamber. Inside the drying chamber, the food products are kept. Inside the drying chamber, there are trays. On the trays, the food products are kept. And then here in the solar air collector, there is a inlet. The air will be collected inside. And then the air will be passed through the solar air collector. It is simple rectangular tunnel only. The air will be entered inside and then heated because of the glass plate. And then because the exit air temperature, now let us assume the air temperature will be around 35 degrees Celsius. Fresh air temperature will be 35 degrees Celsius. After heating, the air temperature will be 70 to 80 degrees Celsius. You can imagine. So if the air temperature will be 70 to 80 degrees Celsius, or the air temperature is increased to 70 to 80 degrees Celsius, because of the free energy, we are not making any electrical energy to heat the air, then it is much beneficial to us. That temperature is used to heat the food product and then the food product is allowed to get the heat and then the moisture is removed on the food product. So this is the case in the indirect solar drying. So here, the fourth limitation that the color degradation is avoided in this setup because here the solar energy will be collected in the solar air collector and then the food product is kept in the drying chamber. Therefore, the direct exposure of sunlight is avoided in the indirect solar dryer setup. So that's why this setup is used in almost all the places, even in Andhra, Telangana, a number of places. And the people are manufacturing and then there are certain companies are purchasing or means fabricating this setup and then selling to farmers. The farmers are using this type of indirect solar drying. Most of the time they are drying ginger, corn, and then chili, even green chili also they are drying. And then like leaves also they're drying. Some medicinal leaves like tulsi, peppermint, like that. Some leaves are also they are drying. And then the dried products are available in the market. Even if nowadays you can see in all the dried shops having almost all the dried vegetables, dried fruits, dried leaves, including curry leaves. Packeted dried leaves you can find on that. So it is one of the biggest success in Telangana and Andhra. Maybe other states also it is there. Tamil Nadu also it is there. You can find these dried products because the products which are dried in the indirect solar drying will be very neat, very fresh, and that can be consumable. If any, even if you pour some water and then we can consume anytime, whether it's a fruit or vegetable. Yeah, whatever I mentioned, it is here. Yeah, some introduction about this. The solar installation is mentioned here. Yeah, this is the setup what we have developed, the indirect solar dryer. Whatever I explained in this last setup that we already developed here. There is a solar air collector. There is a chamber. And this is the 2D diagram we mentioned here. In the solar air collector, you see it's a inclined plate. In the top, you are keeping the transparent glass cover. That means simple window glass cover is kept inside. In the bottom, insulation is provided because whatever the heat trapped inside the system should not be lost. That's why we are providing Rockware insulations. And then we are providing a absorber plate here. Absorber plate. That absorber plate, we are providing not a straight plate, not a flat plate, or not a smooth plate, but we are providing with some corrugations. Triangle corrugations are provided here. You can see the reason is once the air will be entering here, if it's a flat plate, then the air will be heated because of the smooth plate. But in the corrugated plate, the heating of air is more because of the reason is more surface area is there. Because of the corrugation is provided, more surface area is provided. Therefore, because the heat transfer is directly proportional to surface area. And then another one is this corrugation always providing some turbulence, air turbulence. So since the air turbulence will be there, this air temperature inside this SAC tunnel, this rectangle tunnel, is almost like a uniform temperature because the air mixing is taken place very perfectly. And if the air perfectly mixed and then will be reaching to the chamber, this is the drying chamber. Inside the drying chamber, we are keeping the trays. If the air is perfectly mixed and then reached to the drying chamber, then the drying will be perfect and then the dried products also will be uniformly dried. So that's why we are providing the corrugated absorber plate. So now we need to solve this problem. How CFD techniques will be helping to solve these problems in the. Okay, so initially, when the product is dried, we are keeping the food products in the tunnel, sorry, in the trays of the drying chamber. When the food products are getting heated and then losing its moisture, it's a simultaneous heat and mass transfer process. Actually, drying is a simultaneous heat and mass transfer process. So during the process, the food is getting heated and then it's losing its moisture. Okay, so that aspect is modeled in CFD. So here we are keeping a single rectangle piece of food product. So let us assume a potato cube. And then we are not taking the lot of potato slabs. We have taken only one potato slab. And then the potato slabs are kept inside a test section. Let us assume this is a wind tunnel test section. And then we are sending the hot air from one end to other end. Okay, so it's almost the same problem is approximated in this way, and then the food product is kept. Here also the food product is getting exposed by supplied air. Here also the food product is supplied by the exposed air. So the air will be entered inside, and then this is a heated air. Let us assume this is 70 degrees Celsius here because in this setup, the outlet temperature is 70 degrees Celsius. So the 70 degrees Celsius is entering inside, and then the food product is getting exposed by the hot air, and then finally the outlet, the hot air is coming outside. So this problem is solved, and then if the problem is solved with the help of continuity equation, momentum equation, and then energy equations, then we can identify how the uh, velocity profile inside or the air profile inside, how the pressure distribution inside, how the temperature distribution inside the tunnel, then we can identify it, because this type of analysis will be helping us uh, how the properties of these fluids and then how the product will be getting heated. So that's why this problem is solved in the CFD case. So now based on that, we could able to get the velocity distribution. Sorry, this is temperature distribution inside the tunnel. So the tunnel, this is a tunnel, test section tunnel. Here we are keeping the food products. It's a rectangle object. The air is sent from here, left to right. This temperature condos, yeah, at a different velocity, because we varied the inlet velocities also, 2 meter per second, 4 meter per second, 6 meter per second. For different velocity conditions, how the temperature profiles look like, that we could be able to solve with that here. You can see how the profiles are looking here. When the velocity is 2 meter per second, the temperature profiles are almost like a symmetrical, but slight wavy nature is there. When the air temperature is, sorry, when the air velocity is 4 meter per second, the symmetricity will be slightly varied. But anyway, the profile is almost like a stable profile. When the velocity will be increased to 6 meter per second, then the profile will be almost the 4 and 6 meter per second is almost the same, but the boundary layer developed over the food product is slightly less because of the higher velocity. Now, this is the velocity distribution over the food product. Okay, at 2 meter per second, how the velocity look like? You can see the 2 meter per second is almost like the wavy nature is coming. That means the flow instability is coming and then the air will be moving. When it is 4 and 6 meter per second, the profile is almost like a symmetric profile. You can see on that. And then you can see when the air will be reaching near to the surface, inlet surface. Let us assume this is the inlet surface and then this is outlet surface. When the air will be reaching and then hitting the inlet surface, and then there the velocity will be around 1 meter per second. But when it is just behind the object, you can see the velocity almost 0 meter per second, or sometimes negative velocity. There is a chance now when the air will be flowing over the object, wherever it is hitting hardly, then those places the velocity will be there. There is a place, a wake will be formed just over the object. That's why somewhere the negative velocity is found on that. So these type of studies will be helping us how to the heat transfer will be taking place, how the mass transfer will be taking place from the product. These can be evaluated with the help of CFD simulations. So here there is nothing to explain because 4 and 6 meter per second is always producing uniform temperature profile and then symmetric velocity profile. So now in the part of the CFD simulations, whenever we will be keeping the food product inside a tunnel, it is getting heated and then the moisture is removed. Then one important parameter is involved here. That parameter is called heat transfer coefficient. Convective heat transfer coefficient. You maybe remember on that. It is usually denoted as H. It is watt per meter square Kelvin. So how the heat transfer coefficient will be, or what are the values of this heat transfer coefficient on different surfaces? So that we wanted to know because that is one of the effective parameter which is helping to know how the heat transfer will take place, how the mass transfer will be taken place. So that's why we estimated the both values, heat transfer coefficient as well as mass transfer coefficient value. That is plotted in these plots. You can see this is the food products, and then when the food product is kept here, initially the air will be uh, flowing and then hitting the inlet surface. Then how the heat transfer coefficient values will be on the over the distance of the food product. The distance is 4 into 2 into 2 centimeter. So now I plotted the heat transfer coefficient value with respect to the depth of the food product, 2 centimeter. Okay, the values are on that At 2 meter per second, the values are from approximately 68 to almost 50 watt per meter Kelvin. At 4 meter per second, it's almost 70 to 78 watt per meter square Kelvin. At 6 meter per seconds, the values are almost from 80 to 84 watt per meter square Kelvin. So from this analysis, we can get the awareness here on that. When the velocity is increasing, the heat transfer coefficient is always increasing. It is correct only. In the practical also, it is correct. When the air is flowing fast, or if you're putting the fan in the top speed, then the heat transfer coefficient between the human body as well as air will be more. That's why the body will be getting more comfortable. The sweating will be removed quickly. And then heat transfer will be always taken place as well as mass transfer also taken place. So that's why if the velocity is increasing, the heat transfer coefficient is always increasing on the inlet surface. Now, the same thing is plotted for the outlet surface. For different velocities, it is plotted. Here also, when the velocity is increasing, the heat transfer coefficient is increasing. But at the same time, if you compare both surface facing inlet and then surface facing outlet of the food product, the values are, you can see, the surface facing inlet, the values are ranged from 50 to 84 watt per meter square Kelvin. But in the surface facing outlet, the values are lies between 10 to 45 watt per meter square Kelvin. Okay, so the comparatively the surface facing inlet, the surface facing outlet values are less. Already we have seen the air velocity is almost negative value in the behind the surface of the product. So it is reflecting in this heat transfer coefficient also. Okay, so that's why the values are slightly less compared to the surface facing inlet. Similarly, the heat transfer coefficient on bottom and top surfaces and then front and rear surfaces is plotted. The values are varying in a similar pattern. And then the average values are also almost the same only. So there is nothing to explain here. So these values will be giving some input to us that how the drying takes place, how the heat transfer coefficient will be impacting the uh, drying process or the simultaneous heat and mass transfer process. So like that we can get the information, and that such type of results are very rich for drying processes. So the drying industry is always studying these studying these values, and then accordingly they are identifying how to manufacture the solar dryer, and then they're making the values because these values are necessary for some modeling purpose, mathematical modeling of drying problems. So now this one is heat mass transfer coefficient. Heat transfer coefficient, actually heat transfer coefficient and then mass transfer coefficient almost a parallel parameters, almost a similar physics is behind on that. How much the heat is transferred, so here it is how much the mass is transferred, like that. Therefore, the values are different, but the nature is almost the same. Okay, so this profile and then this profile, nature is almost the same, but the values are, these are almost 0.0 to 0.08 meter per second. Yeah, now the mathematical modeling, how it was done, it is mentioned here. So we solved the heat transfer equations because it's a three-dimensional problem. Therefore, we have taken a three-dimensional heat transfer equations and then three-dimensional mass transfer equations. These two equations must be solved simultaneously because this D is a function of temperature. That means let us assume this is equation number 1, this is equation number 2. This D, the D which is situated in equation number 2 is a function of equation number 1. That's why. So whenever we will be solving the second equations, without the help of the first equations, we cannot solve it. Okay, the first equation belongs to heat transfer, second equation belongs to mass transfer. So these two equations must be simultaneously solved. This is heat transfer equation, this is mass transfer equation. That's why it is called the simultaneous heat and mass transfer equations. In practical also, the heat and mass transfer process, example, the drying process cannot be separately explained. We have to explain the heat transfer as well as mass transfer simultaneously. In the mathematical case also, both equations must be solved simultaneously. Then only we can get the temperature and moisture distribution inside the product. Okay, so here these are the boundary conditions we need to use. you can see there is a value of H here. So this H only we already found and then plotted here. So this H we have estimated, and then by using curve fitting solutions, we incorporated in these equations, and then we have solved these equations and then got the temperature distributions. Similarly, this is the mass transfer boundary conditions. So here we need the help of mass transfer coefficient. The mass transfer coefficient is taken from these plots and then incorporated here in terms of curve fitting equations, and then this mass transfer equation is solved and then moisture distribution is found. So these are the, yeah, here we mentioned 6 equations because since it's a 3-dimensional problems, we need to give 6 boundary conditions. That's why these equations came on that. Yeah, I told that D is a function of temperature. D is equal to D naught into exponential of minus 999 by temperature. So if you wanted to solve this D, then it is a function of temperature. Okay, so that's why I told it's a simultaneous heat and mass transfer process. So these are the assumptions we considered. Moisture content independent thermophysical properties, negligible shrinkage or deformation of the material during drying, negligible heat generation inside the moist object, and the negligible radiation effect. We didn't consider the radiation part. Actually, this problem we solved in 2007-8 times because those days the computers are not very effective to solve these equations. If you, because this itself is taking almost 7-8 hours, since it's a 3-dimensional case, each simulations will take 7-8 hours. But nowadays, very costly computers came. So because of that lack of computers only, we couldn't add the radiation effects. You can add radiation effects also, then the code will be a little complicated. Maybe present days computers can be able to solve it, but it's a little difficulty only, but we can able to solve it. So now I could able to visualize the temperature distributions inside the food product. I told it's a rectangle object is kept in the tunnel. In this case, you remember on that, there is a rectangle object is kept inside. I hope the PPT is perfectly visible and then my voice is also audible. Can anyone say that? Can I continue? Okay, yeah. So here we could able to get the temperature distributions, able to get the temperature distribution on the food product on different slices because we have taken one slice, but any slice we can get the temperature distribution because if you solve the problems in CFD, actually, yeah, this problem is solved by writing a computer code by using Fortran 9D. So those times Fortran, I think Fortran 83, I think Fortran 83. A computer code was written for both simultaneous heat and mass transfer process. It is almost 3,600 line computer code. And then anyway, it's not necessarily the code can be written in Fortran. You can write in any software by MATLAB or Python or C++ or whatever it is. In MATLAB, some inbuilt options are there. Some matrix can be directly taken by calling the subroutines. Then you can solve it in the MATLAB also. So here we solve the problems and then we could able to get the temperature distribution for different times. 0.167 hour means 0.167 hour means how much? I think it's 20 minutes or 10 minutes. Yeah, 601 seconds. That means, yes, 10 seconds. Sorry, 10 minutes. This is for 10 minutes. The temperature distribution for 10 minutes. And this is 0.5 hour means 30 hours. Sorry, 30 minutes. 1 hour, 2.5 hours. Like that, these values are taken for velocity at 2 meters per second. Air temperature is 60 degrees Celsius. There is a slice at 0.01 meter. That means at the middle of the slice we have used. And then you can find on that for different times, the temperature of the food product is always increasing. Could you notice on that? Here, if you take the left side of the food product, the maximum temperature is 320 Kelvin at 10 minutes. it is increased to 328 Kelvin at 30 minutes. It is increased to 332 Kelvin at 1 hour. It's increased to 333 Kelvin at 2.5 hours. Okay, at the surface facing inlet. But the other edge, the temperature is less only. That's anyway true only because we are sending the air in one side. The other side will not be will not be heated that much. That's why the minimum temperature. Hello, that is the reason. The minimum temperature is around 306 degrees Celsius. Uh, but the minimum temperature always increasing for different times. At 10 minutes, it's 306 Kelvin. At
rainbow color.
At 30 minutes, it is 322 Kelvin. At 1 hour, it is 330 Kelvin. At 2.5 hour, it is 333 Kelvin. Like that, the temperature is always increasing with the different times. It is natural. Whenever we will be drying the food products, it's a time-consuming process. It is taking its own time. And when the time is increasing, the product temperature is always increasing. So that naturality, we could able to get it through this software, through the programming softwares. And then finally, the results are plotted in the TechPlot software. So this is the place we could able to get the temperature distributions. So this is for velocity 2 meter per seconds. And then similarly, we could able to get the moisture distributions inside the food product. Moisture distributions. Okay, so already I told it's always a heat and mass transfer process. When we are solving the heat transfer equation, we will be getting the temperature distributions. When we solving the mass transfer equations, we will be getting the moisture distributions. Okay, so let us assume the time is 1.5 hour. That means 1.5 hour. Initially the surface moisture is reduced. You see, the initial moisture content of the food product is 4.88 kg per kg of dry basis. Let us remember 4.8 value. You can see the surface it's almost 1.4 kg per kg of dry basis because it is taken at after 1.5 hours. At the same time, the inside the food product, the moisture is not removed. You can see. So inside the food product it is 4.5 kg per kg of dry basis. It means that the food product is always dried from the surface and then the interior moisture content will be diffused towards the surface and then from the surface again the moisture will be removed. The same thing I explained in the introduction of the drying. Okay, so that aspect also perfectly reflecting in this moisture distribution of the food product. So here you can see the inside moisture content is more, the outside moisture content is less. Okay, when the time is increased to 5 hours, now the inside moisture content is the maximum moisture content is reduced to 4, the outside it is 1.2. That means still the excess moisture content in the food product is diffused to the surface and then from the surface again it is removed. Now again the 4 is reduced to 2.6 kg per kg of dry basis at 10 hours. This is 1.5 kg per kg of dry basis at 15 hours. Okay, so it is taking almost 15 hours to dry the food products at 2 meter per second at 60 degrees Celsius. If the conditions will be changed, then we will be getting better answers. We will see if we have the better answers. Yeah, like that I didn't present other data, other temperature distribution, moisture distributions for different velocities, 4 meter per second and 6 meter seconds, and then different temperatures. This is 60 degrees Celsius. We solved 70 degrees Celsius and then 75 also I think we solved it. I'm not producing all the results. What we wanted to convey is similar way, all the food products can be taken and then the mathematical expressions can be used and then we could be able to visualize the temperature and then moisture distributions with the help of our basic governing equations. So now this is another one equations we solved. I think it is a green piece. Anywhere I mentioned or not? Green piece. Yeah, maybe it's a green piece. Spherical food products. Green piece means Pachai Patani in Tamil, and then Telugu it is, what is Telugu? I don't know. Green piece, yeah, green piece is solved, and then here could be able to get the temperature distributions for different uh, times 0.1 hour, 0.2 hours, 0.25 hours, 0.5 hours, 0.6 hours, and then how the temperature is increasing inside the green piece is plotted. The actually it is plotted with the non-dimensional temperature. That's why the values are in terms of 0 point like that. So the here also the red part means the surface of the food product, surface of the green piece. It is the surface of the surface temperature of the green piece is more. The blue part is less temperature because it's inside the product. Initially, it will not be heated. So like that, the plot is drawn for different temperatures. Now this is the moisture content distribution inside the green piece. Actually, green piece is not like a perfect sphere, but we assumed it's a perfect sphere and then we solved the spherical equations. We solved the spherical equations. Previously, we have taken Cartesian coordinates since it's a rectangle potato is taken. This green piece is a spherical, almost 95% sphericity is there. That's why we assumed 100% sphericity and then we modeled as a sphere and then we could be able to get the temperature distribution inside on that. Okay, so this one already explained what are the different accessories of the solar dryer. Yeah, now we could able to apply the CFD concept in the setup itself, and then how the corrugations will be helping us to improve the heat transfer. Here we have given the triangle corrugations, and then different corrugations are there in the literature, like spherical corrugation, sorry, like wire tape corrugations, rectangle corrugations, like zigzag corrugations. There are number of types of corrugations are there. So that also we are solving one by one by using the CFD techniques, and then almost all the works are published and then still we are working on that. So here instead of a triangle corrugation, we are providing the square corrugations. Actually, the corrugation whatever we kept here, the same problem is taken and then we are solving here. Actually, here the corrugation is on the bottom side of the solar air collector, but here we are providing the corrugations on the top of the solar air collector. Almost both are same only. We are slightly tilting the device and then we are doing the CFD analysis. 1 minute. I will be checking my battery level. Yes, it is coming down. So 1 minute break I will take. I will connect the computer. And the paper until you have to that in mark on this. That one here, that one the paper is very clear. Paper analysis mari. Deal la. Ito mani am. Okay, yeah. Sorry for the disturbance. Okay, can I continue, sir? Yeah. So here we are providing the corrugations, square corrugations on the top of the plate, and then we are sending the air. The remaining thing is everything is same. We are assuming here 1,000 watt per meter square of solar insolation will be reaching to the surface, and then we have taken some entrance section, test section, and then exit section. The air is sent in on inlet, and then air is sent outlet, and then actually, this is the zoomed view of the two consecutive square ribs. The distance between the two square ribs is pitch. The pitch is varied in our case. In what pitch we will be getting the maximum heat transfer. That was estimated through the CFD analysis. And then this height also varied. Pitch height, taken as a small e. So these things we varied and then we could be able to provide the optimized pitch and then height of the square corrugations. And then from that we could able to make some uh, equations, usually called some equations we have generated in terms of Nusselt number, and those Nusselt numbers are used directly, can be used for in your system, and then we can estimate the heat transfer coefficient or whatever it is. So this is the CFD condor plots, how the velocity profile looks like on over the this each and every square ribs or square corrugations. Okay, when the air is flowing like that, the square corrugations always will be, you can see in the zoomed view is mentioned here. Near the square corrugations, the air fringes are formed. Air fringes are formed, and then because of continuous corrugations, the air will be always getting mixed with each other. Air molecules always will be mixed with each other, and then we will be getting almost a uniform temperature inside the duct because of the turbulence nature. So this is one of the uh, good condor plot we have observed through the CFD simulations. These are the input values. The Reynolds number is 15,000, and then P by E means pitch by height is taken as 7.14. This is for 7.14, and then this is for another pitch. Actually, the pitch and then heights are varied. So like that, we done the analysis through the CFD, and then finally we could able to give the optimized pitch and then optimized height, and then which case we have another one parameter called thermal enhancement parameter, or otherwise called thermohydraulic performance parameters, THPP, and then where the Nusselt number is more. Okay, whenever you will be keeping the corrugations, the friction factor will be more. That must be avoided. Our ultimate aim in this CFD problem is Nusselt number must be more and then friction factor must be reduced. Okay, so by we have to balance these two parameters, and then we can estimate another parameter called a THPP. And then based on the THPP parameter, we can decide this particular pitch and then this particular E can be preferred for the solar air collector industrial applications. So these already we solved, and then we could able to solve a number of corrugations like square corrugations, triangle corrugations, and then another one is now arc-shaped corrugation is solved by my scholar nowadays. So this work is still going on that. Some experimental studies are there, but numerically there is no studies. Experimental, we know the limitations because we cannot do much experiments and then we cannot get much data. But in the numerical, we can get enormous amount of data, and then we can generate more theories based on the result analysis. That's why the numerical analysis with the help of CFD tools always necessary for the R&D purpose work or your project work. So here we have done another one simulations. This is the solar dryer, means the solar drying chamber, and then this is the solar air collector. We made two models. One is a smooth solar air collector and another one is corrugated solar air collector. If you are providing corrugations, how the temperature profile inside the drying chamber, that type of study was done already. There we could able to find out that if you see these two systems, so in this system, the most of the left side is almost having a lower temperature, and then right side is almost higher temperature. When we are providing the corrugations, the mixing is taken place. You see inside there is a mixing is taken place. That's why the corrugation always helping not only inside the solar air collector, inside the solar drying chamber also, the air mixing is taken place. Therefore, the product will be dried uniformly. So this study also we done, but we couldn't go for a publications because there are some problems with the simulations because it is one of the 3D simulations. We need more sophisticated computer to run this type of simulations. Yeah, and another one study we done on that. If the corrugation is smooth one, smooth means theta is equal to 0 degree. The angle of the corrugations will be 10 degree, 15 degree, 20 degree. These things we studied, but we couldn't find much phenomenal development. But anyway, I mentioned here, maybe it will be useful to you. You can also do similar type of simulations. If you change the angle again, do some better, and then sometimes if you get say a better mixing of the air, then that make good result actually. Yeah, this is the inclination angle. Theta to 20 degree, 10 degree. 10 degree is almost giving some good mixture. 15 degree also it is okay. This also drying chamber temperature distribution inside on that. So now this is the first setup solar dryer. Whatever I explained, we done almost 10 problems in the 10 CFD problems. All the works are already published. So still there is a lot of hope on the solar dryer problems on with the help of CFD. The next work is solar updraft tower. So before going on that, sir, shall we go to the all the topics and then finally the question session can be kept, or in between we can kept, sir?
So we can finish it after. Then at the end of the session, we have.
Oh, okay, we will go on that. Okay, so the next setup is called solar updraft tower. This is also we developed in our laboratory. Laboratory means it's not laboratory, it is the rooftop of a building, it is developed, solar updraft tower. Actually, this setup was developed in France. The name is called Manzanares. The city name is called Manzanares. They developed this plant in around 1985. 1985, and then the chimney height is actually this is the tower or chimney. The chimney height is almost 194 meters. They didn't construct actually. Some portions of the chimney is constructed, and then some portion they taken the help of a real hilltop, because this plant was developed in a hilltop. In the hilltop, there is a natural chimney tower is there, or in a evacuated or not evacuated, like a hole is there in the hill. There is a hole is there, and some places they are occupying by providing some chimney, and then other places it will be natural hill will be there. But in 1985 they developed, and then 1990 the plant was collapsed because of a heavy wind. So now there is no real plants all over the world, but there are some rooftop uh, plants are there, including NIT Warangal. We have developed this SUT plant. Actually, the concept is very simple. There is actually this is a two-dimensional diagram, but imagine this like a three-dimensional diagram, just like a 360-degree circular solar air collector. Circular solar air collector. This plate is solar air collector. Just imagine just a 360-degree. And then in the center, there is a opening place. In that opening, we are providing the tower. Tower are called chimney. Okay, let us assume this is the ground surface. The bottom line, the black surface line is a ground surface. On the ground, we are keeping the solar panels with some inclination. You see there is an inclination. The solar panels are kept in a circular way. And then you can imagine in between there is a air gap. So the air can enter inside, just like a canopy. This is the plan. This is the real plan we have developed. So this is the air inlet. This is the solar air collectors. And then in the center, we are providing the chimney. Chimney means it's a simple cylindrical tower is provided at the center. What will happen means when the air will be entering inside, solar air collector means it's a normal glass plates only, window glass, whatever we have seen in the solar dryer. A similar glass cover is kept here. The air will be entering inside, and then because of the solar air collector, the work of the solar air collector, it will be collect the solar energy and then it will be transmitted inside the tower. Therefore, the air entered inside the tower will be getting heated. So whenever the air will be getting heated, what will happen? What about the density? The density will decrease. Okay, so let us imagine just as a circular device inside the domain. Let us imagine this is almost like an umbrella shape or a canopy shape. The air will be entered inside. Therefore, the air will be heated because of the solar air collector. When the air is heated, the density will be coming down. Therefore, inside the domain, the density will be low. outside air, the fresh air, the density is higher. Okay, then what will happen? Outside fresh air will be there, higher density air will be there. Inside the lower density air will be there. Therefore, the higher density air always will be trying to occupy the lower density place, lower density region. Okay, so this is the higher density air always entering in the lower density air. Therefore, naturally a draft will be created inside. That draft means the air will be naturally flows inside. Okay, because the heated air will be losing its density, then it's always trying to move up towards the tower. Therefore, the natural vacuum will be created inside, fresh air will be entered inside like that. Okay, so this is a simple concept. When the air will be automatically encouraged inside the tower, we can keep a turbine. We can keep turbine here, or in this 2D diagram, we are keeping the turbine here, one inlet and then one is here. Whatever we developed, the turbine is kept here in this location. Okay, so when the air will be entered inside and then naturally the flow is generated and then the turbine can be run, the turbine can be rotating, and then from that, because the kinetic energy of the working air will be converted into mechanical energy because the fan is rotating now. From that, we can extract the electrical energy by providing the natural provisions. This is the actual work. So this is first time invented in 1945 for some other applications, not for electrical applications. And in 1985, the people developed the plant, but it was collapsed. And at present, we have developed this setup in NIT Warangal. So this is the only one setup all over the world now. So this is the setup we have developed. It is almost the diameter of the this canopy part is almost 2.5 meters. The height of the chimney is 6 meters. It is kept on the rooftop. On the bottom of the this panel, we are keeping some storage material. The energy can be stored if you are keeping proper energy storage material. Here we are using the energy storage material of sand, rock mixes, sand and then gravel mixes. And then top we are keeping a copper absorber plate. Here after the sand we are keeping copper absorber plate. So the copper will be absorbing the solar energy and then will be storing the heat energy with the help of this sand and then gravel. So this is the concept we developed because whenever the sunlight will be there, it will be collected by the glass plates and then it will be transmitted inside, the air will be heated. So the airflow will be always taken place, the turbine always will be rotating, but the system can only run on the daytime only. Okay, so nighttime also we need to run the system. That's why we provided the this thermal energy storage provisions. So the daytime, the air will be heated and then the part of the energy will be stored in the thermal energy storage system. And then after 5 o'clock or when the sunlight is gone, then that time the stored heat energy in this thermal energy storage system will be used to heat the air. And then that heated air always will be, again, the same concept. The density will be reduced, then the natural draft is taken place. So because of the solar energy, the thermal energy storage facility, we could able to run the system round the clock. Even 12 o'clock also we have taken the reading. It is producing proper air velocity. Actually, the velocity noticed inside the system is up to 5.8 meter per second. The maximum velocity is 5.8 meter per second. Actually, if you put the fan with a top speed in our home, then the maximum velocity up to 4 or 4.5 meter per seconds only. But here it could able to produce up to 5.8 maximum velocity, and then the average is almost to 2.5 meter per second velocity. It is enough to run the turbine, and then from that we can able to extract the electrical energy. So these are the different components of the setup, and then my scholars are erupting the setup in the rooftop. Pictures are mentioned here. Yeah, some data were mentioned here. So now we could able to see more theories on the solar updraft tower. Yeah, whatever I told is mentioned in this page. We will go for our CFD part. Yeah, one issue is on that. I told the actual height of the chimney is 194 meters, which is already developed in the Manzana's plant. So it is tough to construct such type of chimneys. 194 meters, you can imagine. You can, 100 meters distance running race ground. Okay, so 100 meters, it's almost height 100 meters. 100 meters itself, it is very tough. But if you want to install or develop a 194-meter height chimney is somewhat very tough. That's why commercial investment is higher. But once you installed, this system does not need any much maintenance. So once it is installed, one-time investment only. Then later, the system always generating power, even in the night time also, because of the solar energy storage facility. And then a few prototypes have recently been constructed and projects are being proposed in different parts of Africa, USA, and Australia. But I don't think so. Those studies are not published. I couldn't be able to get any data about the system developed in these countries. Okay, even the low temperature heat is enough. India's solar installation is enough to generate this type of solar updraft towers. Okay, so already yes, one review work is reported in 2016 by Zhu and then Zhu et al. A popular update with the interview of an informed engineering proponent has been published in National Geographic Channel. One video is there in the National Geographic Channel. Already I have seen that one. There are some design factors must be taken care here. The power output depends on primarily on two factors. One is collector area and another one is chimney height. Okay, the collector area is as large as 7 kilometers diameters. So could you imagine 7 kilometers diameters means 7 kilometers diameters. Such a huge circle is needed. So is it possible in cities and then towns? It is not possible. Okay, but we can make even in cities also some secluded places will be there. 1 kilometer diameter uh, solar air collector is planned, but 7 kilometers is not possible. Then we need some rural areas or some desert areas. Those places we can think about this 7 kilometers diameters plant. And then a largest chimney height up to 1 kilometer. Is it possible? 1 kilometer height chimney. Have you noticed anywhere the chimney height is 1 kilometer anywhere? Any industries? I could be able to see around 500 meters chimney in Hyderabad. There are some coal power plants are there. Cement factories are there. They are using very big chimneys. Whenever you will be seeing naturally, the height may not be visible, but the real height is almost 500 meters. Okay, such type of construction is needed in this case also. Then we can able to extract more amount of electrical power. The working principle already explained, so here it is mentioned. Anyway, this CO2 is almost zero. We are not burning any fuel. There is no combustion. So there is no carbon dioxide, there is no sulfur dioxide, there is no carbon monoxide. Almost zero emissions. Okay, the turbines with a horizontal axis or a single vertical axis turbine can be installed inside the chimney. Okay, and then the energy storage. I already explained here. We are providing the natural storage materials like sand and then gravel. Instead of the sand and gravel, you can provide some water tubes also. Water tubes. If the plant is the solar air collector area is diameter is almost 7 kilometers, then we need to lay a lot of water pipes. Then it is sometimes tough to get that much amount of water. Then that plant must be kept near the seashore areas or in the river shore areas. Then we can get frequent amount of water and then the water can be circulated. So such type of one study I noticed on that with water bags or tubes inside on that. And then one study I noticed with the salt water. Salt water means the plant is kept near the seashore and then therefore they are taking the salt water. And then this solar updraft tower also different types of plants are there. So in the first type, it's a convergent type SUT. The chimney is almost like a convergent nature, converged nature. Okay. And then the second setup, it is almost like a divergent nature. Divergent nature. In the third setup is almost like a convergent divergent nature. Okay, so which setup is effective? Then we need CFD techniques to resolve it, and then we can finalize, we can come to the conclusion on that. Let's say the convergent divergent setup is better, or the convergent is better, or divergent is better. Like that, we can come to the conclusion, and then accordingly, we can generate our own plant. Okay, the concept is almost the same because it's almost like the concept of nozzle or diffuser. Okay, the purpose of nozzle is to increase the airflow velocity. Purpose of the nozzle is to increase the airflow velocity. If the airflow velocity will be more, then the air have more amount of uh, kinetic energy. Then the turbine blades can extract more amount of kinetic energy. Therefore, it can produce more. It can produce more speed. Therefore, we can extract more amount of electrical energy. That is the concept we are using here. Different types of plants are used here. Yeah, now we have used CFD techniques, and then we solved the same problems, and then we could be able to get the velocity distributions and then streamline distributions inside the setup. Okay, so this is the velocity distributions, how the velocity air profile will be looking inside, and then how the naturally the draft is generated, and then how it is flown through the chimney. Here, these things we could be able to see in the CFD simulations. Okay, the system must be modeled using the modeling software, or even the ANSYS, there is a modeling software, or even you can go with the SolidWorks or CATIA. Again, the modeling can be incorporated in the CFD tool, and then we can run the simulations. In the simulations part, we need to run our normal governing equations like energy, momentum, and then continuity equations, and then we could be able to get the velocity and the temperature distribution inside on that. So here, this is the pressure distribution is mentioned. This is the temperature distribution is mentioned. Like that. So from that we could be able to get under how the profiles look like, how the flow nature will be inside the setup. Like then we could be able to get a lot of information on that. So this is the plate temperature, absorber plate temperature. I told in the previous case, there is a absorber plate. Here on the top there is absorber plate. We could be able to get that temperature distribution on the absorber plate. If you are providing heat energy storage materials, without heat storage material, and then with heat energy storage material, with the thermal energy storage material. Okay, if you are providing without thermal energy storage material, the temperature is almost lower. It is around 315, or maximum is 344 Kelvin. Sorry, maximum is 344 Kelvin. But whenever we will be keeping with the thermal energy storage material, the temperature is reduced. The maximum temperature is around 327 Kelvin only. The reason is, if you are providing thermal energy storage system, then whatever the heat will be absorbed by the absorber plate will be convected to the thermal energy storage systems. That's why the temperature will be reduced. Maximum temperature is reduced in the thermal energy storage system. So this study also we already done with the help of the CFD tool. This is effect of TS system on 1 centimeter above the absorber plate. This is the air temperature, not the absorber plate temperature. How the air temperature looks like. So how the air temperature looks like on the just 1 centimeter above the observer plate. So that we could able to get on that. So here also the air temperature is more. The maximum air temperature is more. That is almost 340 Kelvin at the center of the domain without the TS system. But with the TS system, the temperature is 318 Kelvin only. Okay, the reason is same thing only, because if you're keeping thermal energy storage system, the copper plate is absorbing the heat, and then it is transmitting, it is conducting the heat inside the thermal energy storage system. That's why the air temperature will be somewhat less in the with the TS system. Okay, so here we studied the velocity, air velocity inside the system without TS system and then with the TS system. The first one is without TS system, and then this is the with the TS system. the maximum velocity obtained is almost 6.5 meter per seconds when we are considering without TS system. Okay. When we are using the TS system, the maximum velocity is slightly reduced. It is around 5.2 meter per seconds. But at the same time, if you are providing the TS system, the system can be run even after sunshine hours also. Even after 5 o'clock, you can run the system. Okay, even night 12 o'clock or even beyond that also, the system can be run. But if you, without TS system, we cannot run the system. Okay, that is the only disadvantages with the first system. Advantages of the second system can be run for round the clock. So now the minimum and the maximum and the average velocity is mentioned for different chimney heights. At chimney height is 0. That means at the base of the chimney, the maximum velocity is around 5.5 meter per second. Sorry, minimum value is 5.5 and then maximum is around 6.7. Average is 6.2 meter per second without TS. At the same time with the TS, the maximum average is only 3.9 meter per second only. Okay. And then when the height is increased, at the height of 2 meter, the average velocity is 5.8 meter per second at the without TS, and then it is reduced to 3.7 meter per second with the TS system. When the chimney height is 4 meter, it is 5.8 meter per second. There is not much difference is there, and then average also 3.7 meter per second. There is not much variation is there. So now the influence of the chimney height. Actually, in our system, we developed up to 6 meters only. If the height is increased beyond on that, how the air velocity will be increasing? So 3 different locations at the inlet of the chimney base, and then inlet of the system, chimney base, and then outlet of the chimney. Like the 3 locations, we estimated the air velocity for different heights. So you can see when the height is increasing, the air velocity is always increasing. You see in this case. It means on that, if the height of the chimney is increased to 10 meter, 20 meter, 30 meter, 50 meter, 100 meters, 200 meters, we'll be getting an enormous amount of air velocity. That is the conclusion here we could able to get on that. And then the collector roof angle. Okay, so here the collector, there is angle here. This angle we adjusted for different simulations. It run for 10, 20 degree and then 25 degree, 30 degree, 35 degree, like that we done different cases. There is not much variations in the maximum air velocity. So it shows that actually this angle we have chosen based on the Warangal's latitude and the longitude. If you wanted to run the simulations for your city's latitude and longitude, and then slightly the angle may give some impact. But we couldn't get much impact. So based on that, if the 30 degrees giving maximum value, maximum air velocity, then we can consider the 30-degree angle, collector angle. The effect of observer plate diameter on velocity on air. Actually, the diameter whatever we have chosen is 2.5 meter. But if the diameter is increased from 3 to 12 meters, 2 to 12 meters, you can see the air velocity is always increasing. Okay, therefore, that's why in the theory they told that there are 2 important parameters are there. One is diameter of the collector and another one is height of the chimney. Yeah, now I could able to estimate the volume flow rate, velocity, theoretical power output, actual power output, overall efficiency, and then chimney efficiency for different chimney heights. When the chimney height is increasing, the theoretical power output always increasing, actual power also always increasing, overall efficiency always increasing, chimney efficiency always increasing. Okay, it shows that if you take a good height, then we can able to get a very good overall efficiency on that. Anyway, these heights could able to produce very small power output only. The maximum is 3.3573 watt theoretical power. Actually is 0.238 watt only. If the height is increased, we can get a good. We can do the simulations for those things also. We can estimate the overall efficiency. Yeah, this is the case. We estimated I think this is the temperature profile for different inclination of the chimney. So this is a straight chimney. The angle of divergence will be increased. Or maybe the title is disturbing me. Yes. 1 degree, 2 degree, 3 degree, 4 degree, and then 5 degree. If the angle will be increased, then how the uh, sorry, this is only domains. We are not solving the equations. The domains are generated for different angles, and then we could able to get the velocity distribution here. When the angle will be 1 degree, the profile will be almost good, and then almost we are getting a fully developed profile. When it is angle is 2 degree, also it is almost okay. 3 degree, 4 degree. But when the angle between 4 degree and 5 degree, the profile, the air velocity is not able to reach at the top of the chimney. There is always some instability is noticed on the air velocity. Therefore, 4 degree, 5 degree may not be fit. Then we can choose anyone, 1, 2, or 3 degree, and then we can choose the chimney angle. For different chimney angle, how the actual power, theoretical power, and then overall efficiency is varied. Like that, we run the simulations, and then we have got on that 4 degree somewhat better for the theoretical, better theoretical power. It is producing almost 1.35 watt at 4 degree at 600 watt per meter square. If the solar insolation is increasing, then this value is also increasing, but still 4 degree angle is better. If the angle is increased to 5 degree, then the value is started to decrease. Okay, it means that further increase of angle will not help us. 1 minute. So the time is 7:30 or up to 8 o'clock? Hello? Can anyone say the time is up to 7:30 or 8 o'clock?
Sir, up to
7:30, sir.
7:30, sir.
Okay. Okay, then I will go to quickly then. Yeah, here we could able to get the temperature distribution inside on that for different solar flex, 600 watt per meter square, 750 watt per meter square, and the 900 watt per meter square. How the temperature control on the observer plate is looked on that. Overall system efficiency is always increasing when the ambient temperature is increasing. Ambient temperature, we no need to go up to 320 degrees Celsius because ambient temperature in some Arab countries, the temperature is more, up to 55 degrees Celsius or 58 degrees Celsius will go. In India, maximum up to 45 or 47 will be there, but still we done the analysis. It may help for other countries. And then the actual power output is estimated for different temperatures, and then we found on that when the temperature is increasing, actual power output also increasing on that, and then overall efficiency also increasing on that. And the next one is solar vortex engine. Actually, the limitations in the solar updraft tower is we need to make a very high chimney, but in the solar vortex engine, similar type of solar air collector is provided here, but here there is a solar vortex machine is generated. Okay, the air will be, you can see this is the cross section of the solar vortex engine. Whatever the air is heated through the solar air collector will be entered through the this solar vortex generator. There is some provisions are there air for air flowing. So the air will be moving through the blades. It's some fixed blades are there. Air will be moving through the blades, and then always there is a turbulence is created inside, and then the air will be flowing through a top hole. There is a top hole here. In this picture, there is a top hole here. Then the airflow will be entering. Then if you are providing a boundary here, boundary panel, and then inside the boundary panel, we are keeping the turbine, and then the turbine can be rotated. So in the solar vortex engine, there is no need of to make the tall chimney. Yeah, this is the diagram we have made on that. This is the solar air collector plate. This is the solar vortex plate. This solar vortex plate is zoomed in this way. The air will be entered through the slots. These are the air slots with the fixed blades. The air will be entered inside, and then there is a natural tornado. It is called a tornado. A natural air tornado will be generated, and then the air tornado will be passed through the top hole, and then it will be moving like moving through the external bounding structure called EBS. So here, if we keep the turbine in this place. If you keep the turbine here, then the turbine can capture maximum quantum of kinetic energy, and then the turbine can be run. So this is the concept we developed in the solar vortex engine. Actually, still it is in the developing stage. We are not developing a real setup, but we run the simulations. Yeah, this is the concept. This concept was developed a very long time back. Uh, Actually, it was developed, the prototype developed by my card team. They developed a prototype one and then developed a prototype two. And then in the prototype, they have used the agarbatti smoke. And then the smoke is coming towards the top hole like that. So we run the CFD simulations and then we could able to get this type of air profile from the top plate. So we also could confirm on that whatever the MyCard developed, the concept is fit for the real setup. Through the CFD simulation, we could able to get on that. So these are the simulations we could able to run, and then we could able to get the velocity profile like that. Yeah, based on that, we could able to provide different simulations. Yeah, these are the air velocity natures for different slots, different air entry slots. In the circular plate, if you provide 6 slots, then how the velocity looks like, 8 slots, 10 slots, 12 slots, like that we could able to run different simulations. And then finally, we could able to come to the conclusion on that. The theoretical power developed is higher in the 8 slots, 3.45 watt power could be able to generate it. At the 12 slots, it is reduced to 3.28. It shows that more slot is not necessary. So like that, the problems can be extended in any way by using the CFD techniques. So these are the tools usually we are using: ANSYS ICM CFD, fastest 3D, ANSYS Fluent, TechPlot 360, Minitab 16, DataFit 19, and then recently we are using COMSOL also. And then these are the programming tools: Fortran, MATLAB, Python, C++ also we are using. So that's all. So any questions you please raise and then we will answer now. So is it okay?
Sir, it is okay, sir.
It is okay, yeah.
Okay. So, dear participant, now you can ask any questions related to the particular presentation.
Any questions?
Good evening, sir.
Yeah, good evening, sir.
This is Palani from Tamil Nadu, the Rajilaal Gandhi College of Technology.
Okay. Which place, sir?
Okay, sir. Yeah, your presentation is very good and the concept is very, what is that, impressive.
Okay, sir.
Is it possible to commercialize this for making energy?
Yes, that's why. That's why I told you, if you could able to solve it CFD tools with the
Okay.
very high chimneys, SUT plants
Okay.
with the 200 meters, then
Okay.
if you get definitely you will be getting good results, because the present analysis whatever we done is getting good result. Okay. So if you are making with a 200 meters chimney in the CFD problems, then we can solve it. And then based on the results, you can approach the commercialized energy agents or government sectors or any other sectors. Then sometimes it is possible. We can somebody ready to provide the funding, and then we can generate such a big plant in very secluded place or desert areas or in the rural areas. Definitely there is a chance.
Sir,
Okay, sir.
Yeah.
Thank you, sir.
Okay, sir. Yeah.
Any other questions from the participant side?
Yeah, if any more questions are there, you can later you can mail me. My mail ID is mentioned here. We have lot of publications. You can get it from a Google Scholar and or my institute website. You can study it, and then if you have any doubt or if you in future if you wanted to work on that, please approach me in mail or through mobile phone. Yeah, is it okay, sir?
Sir, okay, sir.
Yeah.
So it is, thank you very much, Dr. VP Chandramohan, sir. So really, it is a very nice and wonderful presentation. So I think all the participants really enjoyed the session very well, because as a coordinator of the program, we also learned a lot from this presentation, especially the solar updraft tower. It is a new concept in India. It's the first time you are introducing the NIT Warangal, sir. Really, it is a great thing. Your presentation and the new concept you're starting from. What is the demand of solar? It is the from India. What is the level and all? What is the need of solar energy? So what are the research required? It's a lot of scope for this particular solar technology, solar train technologies. It is really this researcher who are all involved, particularly solar research area. It is giving some insight to do the research in particular area. So from the coordinator side, really thank you for your nice presentation, sir. So future also we will give a lot of this type of session from in our college, in our university also, sir.
Okay, sir. Yeah, welcome, sir.
So thank you for a nice, wonderful presentation, sir.
Okay,
Thank you,
sir.
sir.
Yeah.
Good night, sir.
Thank you, sir. Thank you. Good night, sir. I will cut the call.
Okay, sir.
Okay, sir.
Dear
Thank you.
participant, after 3 minutes, again the session will start.
Dear participants, the feedback form is available in the chat box for the session 3. Kindly fill it. My dear participants, I once again repeat it. The feedback form is available in the chat box. Kindly fill it for session 3. Our next speaker, Mr. Praveen, has joined with us. I request the participants to take 2 minutes break, then we will start the next session. Your kind cooperation is highly appreciated in this regard, please.